Greetings, viewer. Don't forget to visit my website for links to support the production of these works if you value what I'm doing. I appreciate any help you can offer. Thank you for having a look and a listen. Yours, JohnLothe. Understanding Physics, 3 volumes in 1, by Isaac Asimov. Read by JohnLothe. Chapter 6. Momentum. Impulse. Let's consider a falling body again. An object held at some point above the ground is at rest. If it is released, it begins to fall at once. Motion is apparently created where it did not previously exist. But the word created is a difficult one for physicists, or, for that matter, philosophers, to swallow. Can anything really be created out of nothing? Or is one thing merely changed into a second, so the second comes into existence only at the expense of the passing into non-existence of the first? Or perhaps one object undergoes a change, from rest to motion, for instance, because, and only because, another object undergoes an opposing change, from rest to motion in the opposite direction, for instance. In this last case, what is created is not motion, but motion plus anti-motion, and if the two together cancel out to zero, there is perhaps no true creation at all. To straighten this matter out, let's start by trying to decide exactly what we mean by motion. We can begin by saying that a force certainly seems to create motion. Applied to any body initially at rest, say to a hockey puck on ice, a force initiates an acceleration and sets the puck moving faster and faster. The longer the force acts, the faster the hockey puck moves. If the force is constant, then the velocity at any given time is proportional to the amount of the force multiplied by the time during which it is applied. The term impulse, I, is applied to the product of force, F, and time, T, for a formula that reads I equals F times T. Equation 6-1. Since a force produces motion, we might expect that a given impulse, that is, a given force acting over a given time, would always produce the same amount of motion. If this is so, however, then the amount of motion cannot be considered a matter of velocity alone. If the same force acts upon a second hockey puck, 10 times as massive as the first, it will produce a smaller acceleration and in a given time will bring about a smaller velocity than in the first case. The quantity of motion produced by an impulse must therefore involve mass as well as velocity. That this is indeed so is actually implied by equation 6-1. By Newton's second law, we know that a force is equal to mass times acceleration. F equals m times a. We can therefore substitute mass times acceleration for force in equation 6-1 and write impulse equals mass times acceleration times time, equation 6-2. But by equation 2-1, see page 17, we know that for any body starting at rest, the velocity, or v, produced by a force is equal to the acceleration, a, multiplied by time, t, so that a times t equals v, or acceleration times time equals velocity. If we substitute velocity for acceleration times time in equation 6-2, we now have impulse equals mass times velocity, equation 6-3. It is this quantity, mass times velocity, that is really the measure of the motion of a body. A body moving rapidly requires a greater force to stop it than does the same body moving slowly. The increase in velocity adds to its total motion. Therefore, on the other hand, a massive body moving at a certain velocity requires a greater effort to stop it than does a light body moving at the same velocity. The increase in mass also adds to total motion. Consequently, the product mass times velocity, has come to be called momentum, from a Latin word for motion. Equation 6-3 means that an impulse, force times time, applied to a body at rest causes that body to gain a momentum, mass times velocity, equal to the impulse. More generally, if the body is already in movement, the application of an impulse brings about a change of momentum equal to the impulse. In brief, impulse equals change of momentum. The units of impulse must be those of force multiplied by those of time, according to equation 6-1, or those of mass multiplied by those of velocity, according to equation 6-3. In the MKS system, the units of force are newtons, so impulse may be measured in Newton seconds. The units of mass are kilograms, however, and the units of velocity are meters per second. So the units of impulse, mass times velocity, are kilogram meters per second. However, a newton has been defined as a kilogram meter per second squared. A newton second, therefore, is a kilogram meter second per second squared, or a kilogram meter per second. Thus, the units of impulse considered as force times time are the same as the units of impulse considered as mass times velocity. In the CGS system, it is easy to show the units of impulse are dyne second or gram centimeters per second, and these are identical also. Conservation of momentum. Imagine a hockey puck of mass, m, speeding across the ice at a velocity, v. Its momentum is mass times velocity, m times v. Imagine another hockey puck of the same mass moving at the same speed but in the opposite direction. Its velocity is therefore negative v, and its momentum is negative mass times velocity. Momentum, you see, is a vector, since it involves velocity and not only has quantity, but direction. Naturally, if we have two bodies with momenta in opposite directions, we can see one momentum equal to some positive value and the other equal to some negative value. Suppose now that the two hockey pucks are rimmed with a layer of glue powerful enough to make them instantly stick to one another on contact. And suppose they do make contact head-on. When that happens, they would come to an instant halt. Has the momentum been destroyed? Not at all. The total momentum of the system was mass times velocity plus negative mass times velocity, or 0, before the collision, and 0 plus 0, or still 0, after the collision. Footnote. By a system is meant the entire collection of bodies being discussed, in this case the two hockey pucks, considered in isolation from the rest of the universe. The momentum was distributed among the parts of the system differently before and after the collision, but the total momentum remained unchanged. Suppose that instead of sticking when they collided, an inelastic collision, the two pucks bounced with perfect springiness, an elastic collision. It would then happen that each puck would reverse directions. The one with the momentum, mass times velocity, would now have the momentum, negative mass times velocity, and vice versa. Instead of the sum, mass times velocity plus negative mass times velocity, we would have the sum, negative mass times velocity plus mass times velocity. Again, there would be a change in the distribution of momentum, but again, the total momentum of the system would be unchanged. If the collision were neither perfectly elastic nor completely inelastic, if the pucks bounced apart but only feebly, one puck might change from mass times velocity to negative 0.2 mass times velocity, while the other changed from negative mass times velocity to 0.2 mass times velocity. The final sum would still be 0. This would still hold true if the pucks met at an angle rather than head-on and bounced glancingly. If they met at an angle, so their velocities were not in exactly opposite directions, the two momenta would not add up to zero, even though the velocities of the two pucks were equal. Instead, the total momentum of the system would be arrived at by vector addition of the two individual momenta. The two pucks would then bounce in such a way that the vector addition of the two momenta after the collision would yield the same total momentum as before. This would also be true if a moving puck struck a puck at rest a glancing blow. The puck at rest would be placed in motion, and the originally moving puck would change its direction. However, the two final momenta would add up to the original. Matters would remain essentially unchanged, even if the two pucks were of different masses. Suppose one puck was moving to the right at a given speed and had a momentum of mass times velocity, while another, 3 times as massive, was moving at the same speed to the left and had, therefore, a speed of -3 mass times velocity. If the two struck together after a head-on collision, the combined pucks, with a total mass of 4 mass, would continue moving to the left, the direction in which the more massive puck had been moving, but at half the original velocity, -v divided by 2. The original momentum of the system was mass times velocity plus -3 mass times velocity, or -2 mass times velocity. The final momentum of the system was 4 mass times negative velocity divided by 2, or -2 mass times velocity. Again, the total momentum of the system would be unchanged. And what if momentum is seemingly created? Let us consider a bullet initially at rest, and with a momentum therefore of 0, which is suddenly fired out of a gun and moves to the right at high velocity. It now has considerable momentum, mass times velocity. However, the bullet is only part of the system. The remainder of the system, the gun, must gain negative mass times velocity by moving in the opposite direction. If the gun has n times the mass of the bullet, it must move in the opposite direction with 1 divided by n times the velocity of the speeding bullet. The momentum of the gun minus the bullet would then be n times m times -v divided by n, or the mass of the gun times the mass of the bullet times negative velocity divided by the mass of the gun, or negative mass times velocity. If the gun was suspended freely when it was fired, its backward jerk would be clearly visible. When fired in the usual manner, its backward motion is felt as recoil. The total momentum of gun plus bullet was therefore 0 before the gun was fired and 0 after it was fired, though here the distribution of momentum among the parts of the system varied quite a bit before and after firing. In short, all the experiments we can make will bring us to the conclusion that the total momentum of an isolated system of bodies remains constant. This is called the law of conservation of momentum. Something that is conserved is protected, guarded, or kept safe from loss. Of course, it is impossible to prove a generalization by merely enumerating isolated instances. No matter how often you experiment and find that momentum is conserved, you cannot state with certainty that it will always be conserved. At best, one can only say, as experiment after experiment follows the law, and as no experiment is found to contradict it, that the law is increasingly probable. It would be far better if one could show the generalization to be a consequence of another generalization that is already accepted. For instance, suppose two bodies of any masses and moving at any velocities collide at any angle with any degree of elasticity. At the moment of collision, one body exerts a force, F, on the second. By Newton's third law, the second body exerts an equal and opposite force, -F, on the first. The force is exerted only while the two bodies remain in contact. The time, t, of contact is obviously the same for both bodies. For when the first is no longer in contact with the second the second is no longer in contact with the first. This means that the impulse of the first body on the second is force times time, and that of the second on the first is negative force times time. The impulse of the first body on the second imparts a change in momentum, mass times velocity, to the second body. But the impulse of the second body on the first, being exactly equal in quantity but opposite in sign, must impart a change in momentum, negative mass times velocity, to the first. The changes in momentum may be large or small depending on the size of the impulse, the angle of collision, and the elasticity of the material. However, whatever the change in momentum of one, the change in the other is equal in size and opposition in direction. The total momentum of the system must remain the same. Thus, the law of conservation of momentum can be derived from Newton's third law of motion. In actual fact, however, it was not, for the law of conservation of momentum was first enunciated by an English mathematician, JohnLothe, 1616 to 1703. In 1671, a dozen years before Newton published his laws of motion. One could, indeed, work it the other way and derive the third law of motion from the law of conservation of momentum. At this point, you might feel that if the physicist proves the conservation of momentum from the third law of motion and then proves the third law of motion from the conservation of momentum, he is actually arguing in a circle and not proving anything at all. He would be if that were what he is doing, but he is not. It is not so much a matter of proving as of making an assumption and demonstrating a consequence. One can begin by assuming the third law of motion and then showing that the law of conservation of momentum is a consequence of it. Or one can begin by assuming the law of conservation of momentum and showing that the third law is a consequence of that. The direction in which you move is merely a matter of convenience. In either case, no proof is involved and no necessary truth. The whole structure rests on the fact that no one in nearly 3 centuries has been able to produce a clear-cut demonstration that a system exists or can be prepared in which either the third law of motion or the law of conservation of momentum is not obeyed. Such a demonstration may be made tomorrow, and the foundations of physics may have to be modified as a consequence. But by now it seems very unlikely that this will happen. Footnote. Please remember that unlikely does not mean impossible. And yet it may be that with a little thought we might think of cases where the law is not obeyed. For instance, suppose a billiard ball hits the rim of the billiard table squarely and rebounds along its own line of approach. Its velocity, v, becomes negative v after the rebound, and since its mass remains unchanged, its original momentum, mass times velocity, has become negative mass times velocity. Isn't that a clear change in momentum? Yes, it is, but the billiard ball does not represent the entire system. The entire system includes the billiard table that exerted the impulse that altered the billiard ball's momentum. Indeed, since the billiard table is fixed to the ground by frictional forces too large for the impact of the billiard ball to overcome, it includes the entire planet. The momentum of the Earth changes just enough to compensate for the change in the momentum of the billiard ball. However, the mass of the Earth is vastly larger than that of the billiard ball, and its change in velocity is therefore correspondingly smaller, far too small to detect by any means known to man. Yet one might assume that if enough billiard balls going in the same direction were bumped into enough billiard tables, at long last the motion of the Earth would be perceptibly changed. Not at all. Each rebounding billiard ball must strike the opposite rim of the table, or your hand, or some obstacle. Even if it comes to a slow halt through friction, that will be like striking the cloth of the table little by little. no matter how the billiard ball moves, it will have distributed its changes in momentum equally in both directions before it comes to a halt, if only itself and the Earth are involved. A more general way of putting it is that the distribution of momentum among the Earth and all the movable objects on or near its surface may vary from time to time, but the total momentum, and therefore the net velocity of the Earth, plus all those movable objects, assuming the total mass to remain constant, must remain the same. No amount or kind of interaction among the components of a system can alter the total momentum of that system. And now the solution to the problem of the falling body with which I opened the chapter is at hand. As the body falls, it gains momentum, mass times velocity, this momentum increasing as the velocity increases. The system, however, does not consist of the falling body alone. The gravitational force that brings about the motion involves both the body and the Earth. Consequently, the Earth must gain momentum, negative mass times velocity, by rising to meet the body. Because of the Earth's huge mass, its upward acceleration is vanishingly small and can be ignored in any practical calculation. Nevertheless, the principle remains. Motion is not created out of nothing when a body falls. Rather, both the motion of the body and the anti-motion of the Earth are produced, and the two cancel each other out. The total momentum of Earth and falling body, with respect to each other, is zero before the body starts falling, is zero after it completes its fall, and is zero at every instant during its fall. Rotational motion. So far, I have discussed motion as though it involved the displacement of an object as a whole through space, with the different parts of the object maintaining their mutual orientation unchanged. This is translational motion, from Latin words meaning to carry across. It is possible, however, for a body not to be displaced through space as a whole, and yet still be moving. Thus, the center of a wheel may be fixed in place so that the wheel as a whole does not change its position. Nevertheless, the wheel may be spinning about that center. In similar fashion, a sphere fixed within a certain volume of space may yet spin about a fixed line, the axis. This kind of motion is rotational motion, from the Latin word for wheel. It is, of course, possible for a body to move in a combination of these two types of motion, as when a baseball spins as it moves forward, or when the Earth rotates about its axis as it moves forward in its orbit about the Sun. Rotational motion is quite analogous to translational motion, but it requires a change of viewpoint. For instance, we are quite used to thinking of the speed of translational motion in terms of miles per hour or centimeters per second. Furthermore, we take it for granted that if one part of a body has a certain translational velocity, so has every other part of the body. The tail of an airplane, in other words, moves forward just as rapidly as its nose. In the case of rotational motion, matters are different. A point on the rim of a turning wheel is moving at a certain speed. A point closer to the center of the wheel is moving at a smaller speed, and a point still closer to the center is moving at a still smaller speed. The precise center of a turning wheel is motionless. To say that a turning wheel moves at so many centimeters per second is therefore meaningless, unless we specify the exact portion of the wheel to which we refer, and this can be most inconvenient. It would be neater if we could find some method of measuring rotational speed that would apply to the entire rotating body at once. One method might be to speak of the number of revolutions in a unit time. Though various points on the wheel might move at various speeds, every point on the wheel completes a revolution in precisely the same period, since the wheel rotates all in one piece. We might therefore speak of a wheel, or any rotating object, as having a speed of so many revolutions per minute, usually abbreviated as RPM. Or we might divide one revolution into 360 equal parts called degrees, and abbreviate it as a zero superscript, also known as the symbol for degrees. In that case, 1 RPM would be equal to 360 degrees per minute, or 6 degrees per second. As the wheel sweeps out those degrees, a line connecting the center of the wheel with a point on its rim marks out an angle. A speed given in revolutions per minute or degrees per second is therefore spoken of as angular speed. It is possible for rotational motion to take place in one of two mirror image fashions. As viewed from a fixed position, a wheel may be observed to be rotating clockwise. That is, in the same sense that the hands of a clock move. It could, on the other hand, move counterclockwise. That is, in the opposite sense to the moving clock hand. Footnote: it is important to specify from a fixed position, for clockwise and counterclockwise are not absolute terms. A wheel may seem to be turning clockwise to you, but if you move to the opposite side and view it, it will then seem to be turning counterclockwise. The same is true if you speak of translational motion as being left or right, or toward or away. Those are terms that have meaning only with reference to your own position. However, if you speak of north, south, east, or west, those are terms that are fixed with respect to the earth and do not depend on your own position. Therefore, we can speak of angular velocity as indicating not only speed but direction as well. Velocities involved in translational motion can be spoken of as linear velocity, since movement is then along a line rather than through an angle. Physicists use another unit in measuring rotational velocity, the radian. This is an angle that marks out on the rim of a circle an arc that is just equal in length to the radius of the circle. The circumference of the circle is pi times the length of the diameter, and is therefore 2 pi times the length of the radius. Footnote: the Greek letter pi is used to represent the ratio of the circumference, c, of a circle to its diameter, d. In other words, c divided by d equals pi. Although every circle may have a different value for c and for d, the ratio of the two, c divided by d, is always the same for all circles. Therefore, pi is a constant, and it is approximately equal to 3.14159. The circumference must therefore also be 2 pi times the length of the arc marked out by 1 radian. The entire circumference is marked out in 1 revolution, so 1 revolution equals 2 pi radians, or 360 degrees. It follows that 1 radian equals 360 degrees divided by 2 pi, or, since pi equals 3.14159, 1 radian is equal to about 57.3 degrees. Angular velocity is often symbolized by the Greek letter omega. Since this is the equivalent in Greek of the Latin letter v, usually used for linear velocity. For any given point on a rotating body, angular velocity can be converted to linear velocity. The linear velocity depends not only on the angular velocity, but also on the distance, r, of the point in question from the center of rotation. If the distance is doubled for the same angular velocity, the linear velocity of the point is doubled. We can say then that linear velocity equals distance times angular velocity, or v equals r times omega. Equation 6-4. This equation is precisely correct when angular velocity is measured in radians per unit of time. For instance, If the angular velocity is 1 radian per second, then in 1 second a given point anywhere on the wheel sweeps out an arc equal to its distance from the center, and linear velocity is equal to the distance. If angular velocity equals 2 radians per second, then linear velocity equals 2 times the distance, and so on. If we were measuring angular velocity in revolutions per unit of time, then equation 6-4 would have to read linear velocity equals 2 times pi times the distance times the angular velocity. And if we were measuring it in degrees per unit time, it would have to read linear velocity equals distance times the angular velocity divided by 57.3. This is an example of how a unit that may, at first blush, seem to have an odd and inconvenient size can turn out to be useful because it allows relationships to be expressed with maximum simplicity. Torque. It takes a force to set a body at rest into translational motion. Under certain conditions, a force can set a body at rest into rotational motion instead. Suppose, for instance, you nailed a long, flat rod loosely to a wooden base at one end. If you pushed the rod, it would not move as a whole, in a translational manner, because one end is fixed. The rod would instead begin to make a rotational movement about the fixed end. A force that gives rise to such a rotational movement is called a torque, from a Latin word meaning to twist. To continue the use of Greek letters for rotational motion, a torque may be symbolized by the Greek letter tau, which is the equivalent of the Latin T for torque, obviously. A given force does not always give rise to the same torque by any means. In the case of the rod just mentioned, the amount of torque depends on the distance from the point at which the force is applied to the fixed point. A force applied to the fixed point will not itself produce a torque. As one recedes from that point, a given force will produce a more and more rapid rotation and will therefore represent a greater and greater torque. In fact, the torque is equal to the force, F, multiplied by the distance, R. For an equation that reads torque equals force times distance, or tau equals F times R. Equation 6-5. In the past, torque has been referred to as the moment of force, but this phrase is now quite out of fashion. Nor need a torque be produced only when a portion of a body is fixed in space. One can be produced even if the entire body is free to move. Consider a body possessing mass but consisting of but a single point. Such a body can only undergo translational motion. A rotating body, after all, spins about some point, or line. If that point is all that exists, then there is nothing to spin, and only linear motion is possible. It is to such point masses that the laws of motion can be made to apply most simply. In the real universe, however, there are no point masses. All real massive bodies have extension. Nevertheless, it can be shown that in some ways such real bodies behave as if all their mass were concentrated at some one point. The point at which this seeming concentration is found is the center of mass. Where a body is symmetrical in shape, and where it is either uniform in density or has a density that changes in symmetrical fashion, the center of mass is at the geometrical center of the body. For instance, the Earth is an essentially spherical body. While it is not uniformly dense, it is most dense at the center, and this density falls off equally in all directions as one approaches the surface. The Earth's center of mass therefore coincides with its geometric center, and it is toward that center that the force of gravity is directed. The concept of the center of mass can explain several things that might otherwise be puzzling. According to Newton's first law of motion, a moving body will continue moving at constant velocity unless acted upon by some outside force. Suppose that a shell containing an explosive is moving at constant velocity through space, and that at a certain point it explodes. Fragments of the shell are hurled in all directions, and the various chemical products of the explosion also expand outward. This explosion is an internal force, however, one produced within the system in question, and it should have no effect on the motion of the system, according to the first law. Yet the various fragments of the shell are no longer traveling at the original velocity. Do Newton's laws of motion break down? Not at all. The laws apply to a system as a whole, and not necessarily to one part or another taken in isolation. As a result of the explosion, the system has changed its shape. But has it changed its center of mass? The center of mass might be viewed as the average point of the body. If one portion of the shell hurls outward in one direction, it is balanced by another portion hurled in the opposite direction. To be more precise, the vector sum of all the momenta in one direction must be equal to the vector sum of all the momenta in the opposite direction, according to the law of conservation of momentum. This can be shown to imply that no matter how the body changes shape through internal forces, the center of mass remains where it would have been if no change of shape had occurred. In other words, the center of mass of the system moves on at constant velocity, regardless of the explosion that hurled bits of the system this way and that. If a body were under the influence of a gravitational force and following a parabolic path, its sudden explosion would not prevent the center of mass from continuing smoothly in that parabolic path, even though the individual fragments moved all over the lot. This implies no interference by forces outside the system. If fragments strike other bodies and are halted, the motion of the center of mass changes. Again, the effect of air resistance on the multitude of particles after explosion may not be the same as the effect upon the single shell before explosion. This may change the motion of the center of mass. Suppose next that a body is falling toward the earth. Every particle of the body is being pulled by the force of gravity, but the body behaves as if all that force were concentrated at one point within the body. That point is the center of gravity. If the body were in a uniform gravitational field, the center of gravity would be identical with the center of mass. However, the lower portion of a body is somewhat closer to the center of the earth than is the upper, and the lower portion is therefore more strongly under gravitational influence. The center of gravity is consequently very slightly below the center of mass. Therefore, while the difference under ordinary conditions is so small as to be easily neglected, it is better form not to interchange the two phrases. The concept of the center of gravity is useful in considering the stability of bodies. Imagine a brick resting on its narrowest base. If it is tipped slightly and then released, it drops back to its original position. If it is tipped somewhat more and then released, it drops back again. As it is tipped more and more, however, there comes a point when it flops over onto one of its other bases. At what point does this flop over come? We can view the gravitational force as pulling upon the center of gravity of the brick, and upon that point only. As long as the center of gravity is located directly over some portion of the original base, the effect of the gravitational pull is to move the brick back upon that base once the tipping force is removed. If the brick is tipped so much that the center of gravity is located directly over some point outside the original base, the brick drops onto the base over which the point is now located. Naturally, the wider the base in comparison with the height of the center of gravity, the greater the degree of tipping required before the center of gravity moves beyond that base. The more stable the body, in other words. A brick resting on its broadest base is more stable than one resting upon its narrowest base. A cone residing on its pointed end may be so adjusted that its center of gravity will be directly above that point. It will then remain in balance. The slightest movement, however, the smallest breath of air, will move the center of gravity beyond the point in one direction or another, and down it will flop onto its side. A juggler keeps objects balanced upon points, or more accurately, upon very small bases, by moving his body in such a way as to bring the base under the center of gravity again every time the center of gravity moves out of position. Where a body is not uniform in density, its center of gravity is not located at its geometrical center, but is displaced toward the denser portions. An object that is particularly dense in its lowermost portion, bottom-heavy, has an unusually low center of gravity. Even a large degree of tipping will not bring that low center of gravity beyond the line of the base, and on being released the object will return to its original position. On the other hand, an object that is particularly dense in its uppermost portion, top-heavy, has an unusually high center of gravity and will flop over after a slight degree of tipping. Since our common experience is with objects of reasonably uniform density, we are generally surprised at the refusal of a bottom-heavy object to fall over, like those round-bottomed children's toys that spring up again even when forced down to their side, or at the ease with which a top-heavy object topples. Let us now return to our point mass, which undergoes only transitional motion. If we imagine a force directed against a real body in such a way as to intersect its center of mass, then that real body behaves as a point mass does and undergoes a purely translational motion. Thus, a falling body is subjected to the pull of gravity directly upon the center of gravity, usually equivalent to the center of mass. Therefore, provided a torque is not applied to the body at the moment of its release, and that the effect of wind and air resistance is neglected, a body will fall in a purely translational manner. If, however, a force is applied to a body in such a way as to be directed to one side or another of the center of mass, a torque is produced as well. Such bodies, even when forced into translational motion by the force, undergo rotational motion also. The manner in which footballs, baseballs, and similar objects spin as they move is well known to all of us. It is so difficult to center the force upon the center of mass that it is virtually impossible to keep them from spinning. Naturally, the further the force from the center of mass, the greater is the rotational motion compared with the translational motion. A coin standing on edge can be flicked into a spin by snapping a finger against its rim, but it will turn very rapidly while moving forward only slowly. It is thought that the stars and planets originated by accretion, and the small fragments struck the growing nuclei of the bodies. Astronomers have labored to devise schemes whereby these colliding bodies would be shown as tending to strike more often to one side of the center of the mass than the other, setting up torques that do not average out to zero. Thus, heavenly bodies, however they may move translationally, also rotate about some axis. Conservation of angular momentum. There is rotational inertia as well as the more familiar translational inertia. If a wheel is rotating about a frictionless axis, it will continue to rotate at a constant angular velocity unless an outside torque is exerted upon it. The application of a torque will induce an acceleration in the angular motion. This angular acceleration can be represented by alpha, the Greek letter alpha, which is the equivalent of the Latin a. The units of angular acceleration are radians per second, or radians per second squared. Just as linear velocity is equal to angular velocity times distance from the center of rotation, see equation 6-4, so by the same line of reasoning, linear acceleration, a, is equal to angular acceleration, alpha, times distance, from the center, r, or A equals r times alpha. Equation 6-6. By the second law of motion, we know that force is equal to mass times linear acceleration, or F equals m times a. Combining this with equation 6-6, we can substitute the distance from the center times angular acceleration for linear acceleration, and have a formula that reads force equals mass times the distance from the center times angular acceleration, or F equals m times r times alpha. Equation 6-7. We have already decided that torque, or tau, is equal to force times distance from the center, F times r. This was expressed in equation 6-5 on page 75. Substituting the value for F given in equation 6-7, we now have a formula that reads torque equals mass times the distance from the center times angular acceleration, or the distance from the center equals mass times distance from the center squared times angular acceleration. Equation 6-8. Now, according to the laws of motion as applied to translation, the ratio of the force to the acceleration, force divided by acceleration, is the mass, m. See equation 3-3 on page 33. What if we take the analogous ratio in angular motion, that is, the ratio of the torque to the angular acceleration, tau divided by alpha? By rearranging equation 6-8, we can obtain a value for such a ratio. The formula would now read as torque divided by angular acceleration equals mass times the distance from the center squared, or tau over alpha equals m times r squared. Equation 6-9. In rotational motion, therefore, the quantity m times r squared, mass times the square of the distance from the center of rotation, is analogous to mass alone, m, in translational motion. This introduces interesting differences in the two types of motion. Consider a body moving in a straight line and made up of 1,000 subunits of equal mass. The force required to stop the motion of this body in a given period of time depends only on the total mass. It does not depend on how the subunits are distributed, whether they are packed closely together, arranged in a hollow sphere, in a cubical array, in a straight line, or anything else. Only the total mass counts, and the manner in which the subunits are distributed does not change the total mass. In rotational motion, however, it is not mass alone that counts, but mass times the square of the distance from the point, or line, about which the rotation is taking place. Consider a rotating sphere, for instance, made up of 1,000 subunits of equal mass. Some of the subunits are close to the axis, and some are far away from the axis. Those close to the axis have a small distance from the center, or r, and are therefore a small mass times the distance from the center squared, or m times r squared, while those far from the axis have a large r, or distance from the center, and therefore a large mass times distance from the center squared, or m times r squared. The body as a whole has some average mass times distance from the center squared, which is called the moment of inertia, and this is often symbolized as capital I. The torque required to stop the rotating sphere in a given period of time depends not upon the mass of the sphere, but its moment of inertia. The value of the moment of inertia depends on the distribution of the mass and can be changed without altering the total mass. If instead of a solid sphere, we made up a hollow sphere of the same subunits, some of the subunits previously close to the axis would now be located far from the axis. On the other hand, no subunits would have been moved closer to the axis. The average distance from the center would increase and the moment of inertia, that is, the average mass times distance from the center squared, would increase considerably, even though the total mass had not changed. It would require a much larger torque to stop a spinning hollow sphere in a given period of time than it would to stop a solid sphere of the same mass spinning at the same angular velocity. Thus, gyroscopes and flywheels, in which it is desired to maintain as even an angular velocity as possible, despite torques of one sort or another, are constructed to have rims as massive as possible and interiors as light as possible. The accelerations produced by given torques are then reduced to a minimum because the moment of inertia has been raised to a maximum. It is not surprising, considering the analogies between rotational and translational motions, that experiment shows such a thing as a law of conservation of angular momentum. By analogy with the law of conservation of momentum in translational motion, this additional law might be stated as: the total angular momentum of an isolated system of bodies remains constant. But how would we define angular momentum? Ordinary translational momentum is mass times velocity, or m times v. For angular momentum, we must substitute moment of inertia, capital I, for mass, and angular velocity, omega, for translational velocity. Angular momentum, then, is equal to moment of inertia times angular velocity, or capital I times omega. Again, however, the moment of inertia, the average value of mass times distance from the center squared, can be altered without altering the total mass, and this produces curious effects. Suppose, for instance, that you are standing on a frictionless turntable that has been set to spinning. You are holding your arms extended, a heavy weight in each hand. The axis of rotation is running down the center of your body from head to toe, and the mass of your extended arms is further from that axis than is the rest of you. The weights in either hand are further still. Consequently, your arms and the weights they carry, being associated with large values of distance from the center, contribute greatly to the mass times distance from the center squared, average, and give you a much higher moment of inertia than you might ordinarily possess. Suppose next that while spinning, you lower your arms to your side. The mass content of your arms and the weights they carry is now considerably closer to the axis of rotation, and without any change in total mass, the moment of inertia is greatly decreased. If the moment of inertia, capital I, is decreased, the angular velocity, omega, must be correspondingly increased to keep the angular moment, moment of inertia times angular velocity, constant. In other words, if you are interested in having the product of two numbers always equal 24, then if you start with 8 times 3 and reduce the 8 to 4, you must increase the 3 to 6 to have the new numbers 4 times 6 still equal 24. This, indeed, is what happens. The turntable suddenly increases its rate of spin as you bring your arms to your side. The rate decreases again promptly if you extend your arms once more. A figure skater makes use of the same device on ice. At first, as rapid a spin as possible is produced with arms extended. The arms are then brought down and the body spins on the point of one skate with remarkable velocity. A body that possesses only angular momentum cannot transmit an unbalanced translational moment to another body, for it has none to transmit. To be sure, the turning wheels of an automobile send it forward and give it translational momentum. There, however, an equal momentum is given the Earth in the opposite direction. The two translational momenta add up to 0. No motorist who has ever tried to drive on ice will dismiss that fact. Once friction has decreased to the point where little or no momentum can be transmitted to the earth, the car will itself gain little or no momentum, and the wheels will spin vainly. If you enjoyed this recording, you can find more and support the production of these works at my website, JohnLothe.wordpress.com. That's www.JohnLothe.wordpress.com. Thanks for having a look and a listen. Your friend, John Lothe.